All right, lesson 4.6, section 4.6 in Rosen's text deals with cryptography. So this is quite an interesting section, applying a lot that we've learned, but we've been learning these things to try to get to this section so we can talk about how messages are encrypted and decrypted, including what is used today, the RSA crypto system. So let's just talk about cryptography first. In general, for centuries, people have attempted to send encoded messages using various methods of encryption and decryption. Now, what are called classical ciphers, these are historical methods that have been used in the past, are generally private key ciphers, ones in which the function that encrypts the message and the inverse function that decrypts the message are kept secret, or they try to keep them secret, but they have not been very secure in the past. Cryptanalysis methods can easily break these codes simply by using frequency analysis, which is shown at the bottom of page 296. I'm going to briefly take us there to the bottom of 296 right here. So it talks about how the relative frequencies of the letters, of various letters of the English words are known. We know what the frequencies of letters are in common usage and common messages that are transmitted. And so the E is the most common letter. It occurs 13% of the time. Then the number or the letter T 9% of the time. Then the letter A 8% of the time, and the O 8% of the time, etc. Then the letter I and the letter N. So based on if we have a message that's long enough, based on the frequency of the letters used, we can make good guesses as to what letters go with what encrypted letter. Okay, so in other words, if the most commonly used letter is a G, then G probably is the encrypted letter for the letter E. Okay, because E is the most common letter in the used in messages. So if G is the most common encrypted letter, then G probably coincides with E. In other words, E got encrypted as G, and likewise for all the other letters. Okay. Now, one classical cipher is called the shift cipher, and this was used by Julius Caesar. So Caesar simply shifted letters 3 letters forward in the alphabet, shifting the last 3 letters of the alphabet to the first 3 letters. So X was shifted to the letter A, Y was shifted to the letter B, and Z was shifted to the letter C. Okay, so it used the function f of p equals p plus 3 mod 26. So it added 3 to the number of the letter. So the letter, let's say the letter G, which was 7, or no, actually probably 6. 0 would be A, 1 would be B, 2 would be C, 3 would be D, 4 would be E, 5 would be F, and 6 would be G. Okay, so if you had the letter G, that would be letter 6, and you add 3 to it, that makes 9, and so that would be the letter J, I believe. Okay, so anyway, it would shift it using this adding 3 to the letter. Now, to decrypt the message, you'd use the inverse function, which is p minus 3 mod 26. Okay, so you just subtract 3 instead of adding 3. All right. Now, example 1 shows a message encrypted and decrypted using the cipher and the key, which is k equals 3. The key is what you're doing. You're shifting. Now, if you're shifting it back 3 letters, it would be -3. So the k would be -3 in that case. But Julius Caesar used a key of +3 to move it to the next letter. Encrypting the plain text message, stop global warming, using the shift cipher with shift k equals 11. All right. So first of all, you translate every one of the letters into a number. All right. And so S got translated to the number 18. T got translated to the number 19. O to the number 14, P to the number 15, etc. So it changed all the letters into numbers, all right, in the Z26, which means the integers from 0 to 25, okay. And then we now apply the shift of adding 11 to each one. So if you add 11 to 18, well, 18 plus 11 is 29, but in mod 26, we can't have 29. What's the remainder when you divide 29 by 26? It's 3. So that's why 18 got translated to a 3, or encrypted to a 3. 18 would be encrypted to a 4, and etc. 14 to 25, 15 to 0, etc. All right. So that shows, how it was encrypted. So the encrypted message, or the ciphertext, that's what we call the encrypted message, ciphertext, is this message here at the bottom of that example. All right. And then example 3 shows decrypting the message when it was encrypted with a cipher using k equals 7. So this time, if it was encrypted with k equals 7, that means adding 7. Well, decrypting it, we would subtract 7. And so that's what was done. So they first made the message into numbers, which is there at the bottom of that page. And then on page 296, they shift the letters by going -7. And so it backs it up, and you get the message, experience is a great teacher. And so you can look at that. Include ciphers of the form P plus K, so it includes the type we've been talking about, but it also includes all shift ciphers can be placed in the form F of P equals AP plus B mod 26. In other words, sometimes we don't just add, sometimes we multiply P by a number A and then add. So it's possible that we multiply A times P plus B, and we would get our encrypted message that way. Now, it has to be the case that this function F is a bijection, and that means it's 1-to-1 and onto. So it has to be 1-to-1 for each letter you're encrypting. There has to be just one encrypted letter. Also, it has to be onto, meaning all the letters are used up. And that happens when the greatest common divisor of A, the number in front of P, and the number 26 is 1. If the greatest common divisor of A and 26 is 1, then it will be a bijection. So you have to have that stipulation here. All right, so here's an example. What letter replaces the letter M when f of p is 7p plus 13 mod 26, okay, is used? So you'll notice that 7 and 26 are relatively prime. In other words, the greatest common divisor of 7 and 26 is 1. So they're relatively prime. So this is a bijection. Okay. Now, convert M to an integer first of all. So M is the number 12. Okay. Then you do f of 12, which means we're going to stick 12 in here. So 7 times 12 plus 13. Well, 7 times 12 plus 13 comes out to 97. And if you do 97 mod 26, that brings you to the number 19. In other words, the remainder, when you divide 97 by 26, gives you 19. Okay? So 19 is the letter T. So the encrypted letter would be the letter T. All right? Now, example 4 on page 296 gives a similar example. They use a different letter than the one I did, but it's pretty much the same thing. Now, to decrypt a letter, when you know the shift cipher encryption function, you have to find the number for the letter to be decrypted. So, say it is C, we would have to basically solve this congruence right here, because this is the encryption, and we're trying encryption formula, and we're trying to find what is the P that will cause that when we multiply A times P and add B, that will get the encrypted letter C, okay, or the ciphertext letter C. So we've got to solve that linear congruence. All right, so I'm going to show two examples, one where we do not use the inverse of A, in this case the 7, and one where we do use the inverse. All right, so here's an example. Decrypt the letter J if it was sent by the shift cipher given by this same function that we talked about a minute ago. Now first we must convert J to a number, which is 9. Okay, you start with A as 0. All right. In mod 26, you can only have remainders from 0 to 25. So we have to start the letter A off with 0. All right. Anyway, then the letter J has number 9. All right. So then we solve P in the linear congruence. 7P plus 13 is congruent to 9. So in other words, this 7P plus 13 will be congruent to 9, or in other words, it'll give us a remainder of 9 in mod 26. Now, you can, just like with an equation, you can subtract 13 from both sides. So that's what I did first, subtract 13, and that gives us 7P congruent to negative 4, mod 26. Now, because 26 is the mod, we can add 26, a multiple of 26, because 26 is congruent to 0. Okay, it's congruent to 0, so you're not adding anything if you add 26 in mod 26. You're adding 0. So I can add 26 to the right side of this congruence as many times as I want. So if I add 26 to negative 4, I get 22. I add 26 again, I get 48. I add 26 again, I get 74. I add 26 again, I get 100. And then 126, and 152, and 178. I can keep doing this. But what I'm looking for is a congruence where the number on the right is divisible by 7. If the number on the right is divisible by 7, I can divide both sides by 7. So I go, what we can do is check each of these numbers, and the first few are not, but 126 is divisible by 7. So if I divide 126 by 7, I'll get a whole number, and so I divide 7 on both sides, and that gives me P is congruent to 18 mod 26. So 18 is the original letter that was used to get the encrypted letter J. So thus the letter J decrypts to be the letter S. So it must be the letter S was our original letter with number 18, because when I plug in 18 into here, I will get the number 9, which was the letter or the number for J. All right, so think about that. Another way to do this is using the inverse. Okay, the inverse of the number 7, which is that number in front of the P. All right, so I'll show you how to do this. So it says decrypt the letter X when the encrypting function is the same function we've been talking about. So the letter X is 23. So we need to solve the congruent. 7P plus 13 equals 23. Now, just like we did before, we can subtract 13 from both sides. So you get 7P is congruent to 10 mod 26. All right. Now what we're going to do is use the Euclidean algorithm and then work it backwards to get those benzoic coefficients and therefore basically find the inverse of 7. All right, so here's the Euclidean algorithm. I want to find the Euclidean algorithm using 7 and 26. So 26 is 7 times 3 plus 5, and then you bring down the 7. It goes 7 is 5 times 1 plus 2, and then you bring down the 5. So 5 is 2 times 2 plus 1, and then bring down the 2. 2 is 1 times 2 plus 0. Now we're going to work backwards, starting with this equation in yellow, because we want the left side of this equation to be 1. Remember, an inverse is a number that the product of the original number and the inverse is congruent to 1. So that's why we're using the equation that has 1 in it. So we move the 2 times 2 over to the other side, so we have 1 is equal to 5 minus 2 times 2. And then as we did before, we're going to systematically replace the 2 and the 5, the numbers above the 1 here. So I'm going to replace the 2 here, and I get 7 minus 5 times 2, and you only need to replace one of the 2's. And then you distribute the 2 and this negative sign out in front of the parentheses, and you get 1 equals negative 2 times 7 plus 3 times 5. Now, that came about because if I multiply the 2 times the 1, it becomes 2 times 5, but you have a negative sign here and a negative sign here. Well, that will make it positive 2 times 5, but I also have another 5 here, so that makes it 3 times 5. So you can simplify that and show that it equals this. All right, so then we're going to replace the next number up, which is the 5. And so I replace the 5 with 26 minus 7 times 3. And if I do that and distribute the 3, I get 3 times 26, and I get 3 times negative 3, which is negative 9 times 7. So it's negative 9 times 7. And I add the negative 2 times 7, and I get negative 11 times 7. So why did we do all that? Well, the 3 times 26 is congruent to 0, because in mod 26, any multiple of 26 is congruent to 0. So 3 times 26 is congruent to 0, so I can basically get rid of the 3 times the 26 and just replace it with 0. And so I get that negative 11 times 7 is congruent to 1. All right, so that means that negative 11 must be the inverse of 7. But if I add 26 to negative 11, I can get a positive inverse, basically the number 15. Negative 11 plus 26 is positive 15. And so 15 could be used as a positive inverse of 7. All right. So now I go back to that original congruence we had. 7p is congruent to 10 mod 26. And I multiply both sides by 15, the inverse. And so 7 times 15 is 1, is congruent to 1. So I can replace, the left side and just have 1p. And on the right side, I multiply by 15, I get 150. All right. Now 150, the remainder when you divide 150 by 26 comes out to 20. So that's the answer for the congruence. So we have found that 20 must be the original letter that was used to encrypt it and get the letter X. So we decrypted the letter X and got the original letter U, all right, which is 20. But you could have done that kind of like I did on the previous example, where you're looking at the multiples, adding multiples of 26 until you find one that's divisible by 7. Could have done that as well. All right, now a block cipher basically divides up the message into blocks of M characters and then uses a function to shift the characters in each of the blocks. So if you have this long message, we'd divide up the first several characters and shift them around, kind of like scramble the letters. And then the next block would be scrambled, and the next block would be scrambled, and the next block would be scrambled, etc. And then that would be sent like that. But encrypting the message right away using the transposition cipher based on the permutation sigma of the set 1, 2, 3, 4, 5. And so basically sigma, it's the lowercase Greek letter sigma, is sigma 1 becomes 4, sigma 2 becomes 1, sigma 3 becomes 5, sigma 4 becomes 2, and sigma 5 becomes 3. So what does this mean? This means take letter 1 and make it letter 4, take letter 2, the second letter in the block, and make it letter 1, etc. Take letter 3 and make it letter 5. So we're going to break up the message into blocks of 5, putting the letter X in the end of the block to make it 5, because we don't have 2 full blocks. So the message will be right away and then an X at the end, because that we didn't have 5 letters, but we need to just stick a letter in there, so we stick the letter X in there. But you could put any letter you want. Anyway, using the function given in the problem, we send the first letter to the 4th position. All right, so the first letter is the R, and we're going to move that to become in the 4th position. So you notice that in the final encrypted message, the R is in the 4th position. And then the second letter will go to the first letter. So the second letter was the letter I, and that goes into the 1st position. And then the third letter will become letter 5. So the third letter was G, so that is in the 5th position. So that was done in the first block. And then the same process was done in the second block. So you end up with this encrypted message. Now to decrypt the message, you'd use the inverse function. Okay, now how do you find the inverse function? Well, look over here, back up to the encrypting function. So you'll notice that letter 2 became letter 1. Well, in the inverse function, letter 1 will become letter 2. And so that's what is expressed here. Letter 1 will become letter 2. Now, you'll notice over here, letter 4 became letter 2. So letter 2 will become letter 4 in the inverse function. So you just work it backwards with the inverse function. So I'm just looking at each of these things and switching them around, and then we put them in order so you can more easily find, you know, okay, if I'm looking for the third, from the third letter, what do you do with that? Well, it comes third in the list. Now, much of what we've been looking at in the last few sections are leading up to what we're looking at now: public key cryptography and the RSA cryptosystem. The RSA cryptosystem was conceived years before by Clifford Cox in the United Kingdom. He was working secretly for the government of the United Kingdom in the 1970s, okay? But it was named after Ronald Rivest, Adi Shamir, and Leonard Edelman of MIT. They published it and got official recognition or credit for it, even though Clifford Cox independently had developed it back in the United Kingdom. But this is back in the 1970s, and yet we still use it today because it's so very secure. All right. Obviously, if it was not secure, we would have lost it long ago. We would have stopped using it long ago. So the RSA cryptosystem, every person makes public an encryption key. They give out and publish two numbers: N, which is a very large 400-digit number, and the letter E, which is also a very large number, okay? They publish N and E so that anyone who wants to send them a message can use the N and the E to encrypt a message and send it to them, okay? Actually, their computer does this. It's all computerized, but anyway, their computer sends an encryption key, which is two numbers, N and E, all right? Now, N is the product, N equals P times Q, of two large prime numbers, P and Q. So they have to be prime numbers, P and Q, and these are kept secret. Now, the exponent E is relatively prime to P minus 1, Q minus 1. So you got to make sure that you can't just use any exponent. You got to verify that that exponent is relatively prime to P minus 1 and times Q minus 1, okay? So you'd have to, have a way of testing that. Now, to ensure that the system is secure, the primes P and Q are very large, at least 200 digits long, okay? So you've got to use very large prime numbers there, making the product N at least 400 digits. See, it has to be that large because it has to take a computer a very long time to break N up into P and Q, P times Q. In other words, to factor the number N. And even with modern computing power, it is practically impossible to factor this known integer N into unknown primes P and Q in a reasonable amount of time. It would take like centuries long with today's computer power to break up N into P times Q, because it's such a large, N is such a large 400-digit number, okay? So that's what helps keep it secure. Now, how are messages sent in an RSA crypto system? All right. Now, anyone can send the person a message by doing the following. Of course, their computer would do this, but doing the following. All right. Step 1, you translate your plain text message M into a sequence of integers where each character becomes a 2-digit integer. So the letter A, 0, 0. So you got to have 2 digits. Letter B, 0, 1, C, 0, 2, all the way, etc. Then we combine these two-digit integers into one long string of digits. So you're going to have a very long string of digits created by the message. Okay? But you haven't encrypted it yet. Now, divide the string into blocks, M1, M2, M3, all the way to MK, with an even number of digits in each block, say 2 times n digits. Of course, 2 times n makes it an even number, where 2n is the largest even number, so that the number 252525 ending also in 25, in other words, a bunch of the number has to have the 25 pattern in it, with 2n digits, does not exceed n. All right. Now, let's give an example what that means. Suppose n, your large number, which is the product of p and q, is only the number 359803. Now, of course, that's not very secure. A computer could find the prime numbers that would be the p and the q without much trouble. Now, you look at how many digits that number 359803 has, and you place it in between two numbers 252525 or 25252525, and see where it falls. Now, this would fall in between a 6-digit 25 number and an 8-digit 25 number. And remember, you always have to have an even number of digits here. Now, the 252525 with 6-digit does not exceed the number 359803. So we'd use 2n being 6. In other words, we'll use blocks of 6. Okay, so we're going to take our message and split it up into blocks of 6. Okay, that's how we tell. You base it on how big n is. All right, now the ciphertext C for the plain message M is found by doing this. C would equal the message block, so that would be like first your M1, taken to the E power. Now remember, E was a publicly known number, the exponent, mod n. So n is also publicly known. So the person sending the message would take a block of numbers, as you know, in this case, blocks of 6, and go that number to the E power mod n. And you're going to do that block by block until the whole message is encrypted. Okay. Now, it can be calculated most efficiently by a computer using algorithm 5 in section 4.2. We looked at that where we were taking a number to a power in a particular mod. Or you can use an online power mod calculator. All right. And I'll show you that in a minute. Then you encrypt the message C. The encrypted message C is sent to the intended recipient, which has that public key NE. So it's encrypted, so now you can send it over the internet, and you won't be concerned about it being deciphered. Okay. Okay, let me show you an online power mod calculator. All right, there's a few other online power mod calculators, but Wolfram Alpha, if you just type wolframalpha.com, it gives you a line where you're going to enter some command to calculate, or some calculation here. All right, so what I did here is enter 3456 to the power of 2234 mod 68477. 68477. So It does this to the power, and then it finds the remainder when you divide by 68477. And the result is 58350. All right. Calculating a new one, this time using the exponent. All right, anyway. But that's one power mod calculator that you can use online. There's some other ones as well. All right, back to the slides. So once the message is encrypted using what I just showed you, how does it work that the person who's on the other end, who receives the encrypted message, how does that person decrypt the message? Okay. Now, RSA decryption is performed when D, the inverse of the original exponent that we encrypted it with, which is E, D and E are inverses of each other, mod P minus 1, Q minus 1. All right. That's what has to be. We have to know D, the inverse of E, mod P minus 1, Q minus 1. That has to be known. But you can't find the inverse of E unless you know what this P minus 1, Q minus 1 is, which means you'd have to know what P and Q are. And that's what keeps it secure, because only the recipient of the message will know what P and Q are. All right. And so they're the only ones that will know what the D is. Okay, what the D is, the inverse, because they can calculate it if they know the P and the Q. All right. It's not just the inverse using the mod N, it's the inverse using the mod P minus 1, Q minus 1. All right. Anyway, so this inverse exists because we know that the greatest common divisor of E and P minus 1, Q minus 1 is 1. Remember at the beginning, we had to set E, the exponent, to be relatively prime with P minus 1, Q minus 1. All right. So since D and E are inverses, the D times E is congruent to 1 in mod P minus 1, Q minus 1. And so what that means is there's an integer k such that DE would equal 1 plus, and then 1 is the remainder, k times P minus 1, Q minus 1. All right? So the 1 is the remainder here, and then the P minus 1, Q minus 1 is the mod. So this is a multiple of the mod. All right. Now, if we take C to the power of the inverse, D, but what was C? C was the encrypted message, which, how did we get the encrypted message? Well, we took the original message, the unencrypted message, and took it to the power of E. So I can replace C with M to the E power because that's where C came from. All right. And then M to the power of E to the power of D, that would be M to the DE power, because what do you do when you have a power to a power? You multiply the exponents. But we know that D times E is equal to 1 plus K times P minus 1, Q minus 1. So I replace DE with that exponent, 1 plus K times P minus 1, Q minus 1, and then using mod N. All right, so now Fermat's little theorem comes into play here. M to the power of P minus 1 will be congruent to 1 in mod P. And M to the power of Q minus 1 will be congruent to 1 in mod Q. Okay? So those two little facts are going to be used when we try to simplify this and show that it works out. And so let's look at that. Now we're going back to what we had up here a moment ago, that c to the power of d equals m to the power of 1 plus k times p minus 1 q minus 1 mod n, right? Now, c to the d power is equal to m to the first. Now, where did we get the m to the first? Well, that is right here. We're taking that 1, and so we're going m to the first, and then m to the power of p minus 1, taken again to the power of k times q minus 1. All right? Well, that comes from this right here, because what would this be if I have a power to a power? We'd multiply the exponents, right? And so we'd get k times p minus 1 q minus 1. All right? But using Fermat's little theorem, m to the power of p minus 1 is congruent to 1 in mod p. All right? So that's congruent to 1 in mod p, which 1 to any power is going to be 1. So we'd end up with just m in mod p. And likewise, the same thing happens when you put the q inside the parentheses. We get 1 using this part of Fermat's little theorem, and 1 to any power is still 1. So you get m mod q again. Now, this is where the Chinese remainder theorem, something that goes back centuries, comes into play. Since the greatest common divisor of p and q is 1, because p and q are prime numbers, then by the Chinese remainder theorem, we can say that c to the d is congruent to m in the product of those mods, p times q. And what is p times q? It's n. Okay, so we're back to the plain text message m. All right, we started with c and we decrypted it and got it back to the plain text message m in mod n. And so that's how the RSA encryption and cryptosystem will decrypt the message, okay? But of course, computers are what does these calculations, but all the computer has to know is the inverse D, and so you take the encrypted message C to the power of D in mod P times Q, or mod N, all right? And the reason why it works is what we just looked at in this slide. Kind of interesting, I think, that we use all that, including an ancient Chinese remainder theorem, to come up with this. So let's look at an example. So using n equals 47 times 59. Now 47 and 59 are only 2-digit numbers, and so n will be a 4-digit number. So n comes out to 2,773. So obviously a 4-digit number is not secure at all, okay? But just for a simple example for us to see, we're going to use smaller numbers here in this example, all right? So n we're using is the product of two prime numbers, 47 and 59, all right? Now 47 and 59 are your P and your Q here. And then E, the exponent, is the number 5. We're going to encrypt the message FIVE, 5, and begin to decrypt the message 01170877. Now this is two different problems, really. We're encrypting the message 5, and then the other part of the problem is to decrypt another message, which is 01170877. All right. Now, the solution for the part where we're encrypting the number 5, first of all, we got to figure out how to break up the message into what blocks, what size blocks. And so the number 2773 is between, which is your product of the prime numbers P and Q, 2773, is in between 2525 and 25, 25, 25. All right. So that means the 25, 25 cannot exceed the n value. So we have to break it up into blocks of four digits. So blocks of 4 digits is how we'll do this. All right, so then we take the message 5 using the encryption of A being 00, B being 01, C being 02. And so FI becomes the block 0508, and VE becomes the block 2104. All right, so we've got these two blocks that are 4 digits long. That's our original original message, but in numbers. So what we'll do to encrypt the message is do 0508 to the 5th power mod 2773. Now this is small enough we probably could use a regular calculator and figure out what the mod or the remainder is when we divide by 2773. But you could use a power mod calculator if you want. And then 2104, which is the second part of the message, second block to the 5th power, comes out to mod 2773 comes out to 2697. So our encrypted message is 09702697. All right. So your encrypted message is that. Now, now we're going to look at the second part of this problem where we have to decrypt the message 01170877. So we're decrypting that message. So we first have to find the inverse D of the exponent, the original encrypting exponent E, mod P minus 1, Q minus 1. Now, P minus 1, Q minus 1 is 47 minus 1 times 59 minus 1, or in other words, 46 times 58, which is 2668. So that's the P minus 1, Q minus 1. And we need to find D so that 5 times D is congruent to 1 in mod 2668. Right? Well, this can be done using the Euclidean algorithm, or it can be done the way we showed before, using adding the multiples many times of the mod. So if what this means here, see, FD minus 1 has to equal 2668K for some K. 2668 is the mod, and if I subtract 1 from FD, so this is like 2668 dividing into the difference of the two things that are congruent. So 5D minus 1 equals 2668 times K for some K. Now you can just try adding, a bunch of, or try K equal 1, K equal 2, K equal 3 until we get something that will work. But I found when K is 3, then 2668 times 3 comes out to 8004. And then if I add 1 to both sides of this, we get 5D equals 8005. Now, why did we want that? Well, because 8005 is divisible by 5. I can divide both sides by 5. Now, I have to know that 5 and the mod, which is 2668, are relatively prime. And I know that they are because 5 is a prime number. So I could divide both sides by 5, and I get that D equals 1601. All right, so I can check this by going 5 times 1601, which equals 8005, and that is congruent to 1 in mod 2668. Okay, and you can look at the reasoning there. All right, so we found what D is. D is 1601. And then we now do we take our blocks one at a time, our ciphered ciphertext blocks, which is 0, 1, 1, 7 for the first one, and take it to the power of d and calculate that mod p times q. All right. So we go 117. Now you can drop the 0 at the beginning. So just do 117 to the power of 1601 mod 2773, and that will be your decrypted message for the first block. And then you take the second block, 0877, to the power of 1601 mod 2773, and that will be your decrypted second block. All right. Now you can either use algorithm 5 section 4.2 or an online power modular calculator, and if you do that first calculation, you get 1415, and you do the second calculation, you get 0715, which if you translate that, 1415 becomes NO and 0715 becomes GO. So it's the message no go. All right. So apparently some secret mission was aborted. All right. So that is the RSA encrypted system or crypto system, and it's kind of interesting. We do need that power mod calculator to help us, especially when it gets large, the numbers get large. So, try to do that homework where you're trying to encrypt or decrypt messages using the RSA system. But what's really neat about this is this crypto system is still used even today. And one of my students just last semester had a little thumb drive that had an RSA encryption system on it, and he had to type in a code to get into his thumb drive, and it's even in such a small portable thing as a thumb drive. All right, well, let me know if you have any questions.